So now we are going to discuss about capacitors. Okay, it's very important. Capacitor also has a lot to do with potential, but today we are going to just discuss the basics of capacitors. You'll see that capacitors and resistors are very closely connected. Okay, if we are basically considering any kind of circuit, okay, in the real world, you will see that it is made up of a number of constituents, and three most important constituents for any kind of circuit is a resistor, okay, a capacitor. All three are important to know because it's a part of electromagnetic theory. We'll eventually use them, and the inductor. So these are the components which you can physically see. Okay, these are the components, and their properties are that a resistor will have resistance. Resistor will have resistance. That's the property. A capacitor will have capacitance, and an inductor will have inductance. Okay. So what does it show? It shows that these are the components and these are the properties. Okay, and something is very basic that we already know is that whenever we basically have current in a circuit, it is directly proportional to the voltage. Okay, so that means if I want to replace the proportionality constant, the current is equal to 1 by R into V, which actually tells me what is my Ohm's law. Ohm's law is obviously there in the later part. V is equal to IR. So this is my Ohm's law. This is a simplified way of writing it and remembering it. And actually it means that if there is a change in voltage, there will be a change in current, and it is proportional to 1 by R. Okay, but then this resistance does not depend on voltage and current. Okay, because if you look into this idea of resistance here, if you check for resistance here, R is equal to V divided by I. So it does not depend on voltage and current. Although by looking into it mathematically it does tell that, but obviously it does not depend. Why? Because if the current increases, okay, or the voltage increases, the current will also change. If the voltage decreases, the current will also decrease or change, right? So this ratio will always remain constant. So that means this resistance depends on property of the material. So if you're basically considering copper or silver or maybe a nichrome, the resistances will be different. Okay, so it depends on property of material. Okay, so that means that what kind of property it depends on. It depends on properties like R is equal to rho L by A. That means it will depend on what is the length. Okay, this is a very old concept, small class concept. uh, depend on the length of the material, and it will obviously depend on the cross sectional area. So if I have a wire like this, what will be its resistance will actually depend on resistivity, which is the property of the material. It will depend on what is the length. If the length is more, the resistance is going to be more. Inversely proportional to area. If the area or the cross sectional area is less, the resistance is going to be more. Okay, so that is how it works for a resistor. Okay, in a similar way we can also talk about capacitors. Okay, but what exactly are capacitors and why they are used for? Okay, so capacitors, if you look into any electronic circuit, or if you actually google it, you will see that this is basically nothing but in the form of a cylinder with two leads. There are two plates inside. Okay, this is how it looks, but actually it's nothing but two plates inside. One is, you can charge it positively connected to the anode, and another plate, it is connected to the cathode, and in between obviously there is an electric field in the capacitor. So this is how the capacitor looks like. Externally it will look something like this. Okay, so these leads are connected to the positive and the negative terminal, and you can charge the capacitor. So many a times there are a lot of devices. For example, it's summertime, so I'm using a cooler, air cooler, so that's there. You can consider something like a fan. Okay, or you can consider something like a camera flash, even in your mobile phone also. So when the fan, you just switch it on, it does not start instantly. It takes some effort to start the fan. So it doesn't start immediately with a low current. Okay, what happens is it actually needs a higher energy. Okay, so maybe it will need around 20 amperes of current. So from where it is going to get 20 amperes of current all of a sudden? So this is how the capacitor helps in doing this. What happens is a capacitor, okay, usually stores energy. It will store that energy, and it will give out at one instant. It will store the energy and it will give out at one instant. As a result, the fan will start rotating, or the flash will start working, or the cooler fan will start moving. Okay, so it basically stores energy, and that is how a capacitor is functioning. Okay, so that's the important part about capacitor. Similarly, when we talk about capacitance, see, just like for resistance, it is nothing but written as Q divided by V. Okay, so actually what happens is, if we are talking about a charge inside a capacitor, it will actually depend on how much voltage is being applied. More the voltage, more the charge that actually can be stored. So if I want to replace it with a constant, that would be nothing but C into V. So this C again does not depend on voltage or current, because voltage and current will change proportionately. This C, which is actually called the capacitance, okay, what is its capacity, or what is its ability to store, how much energy it can store, and so on. Okay, so it will actually depend on the property of material. Okay, but resistance was R is equal to rho L by A. Similarly, capacitor, the capacitance is nothing but epsilon naught A divided by D. So as I said, that you can actually have a real capacitor, and capacitor is nothing but we're basically having two parallel plates. Okay, so this is, let's say, the positive plate, and this is my negative plate. Okay, I have a distance between these two plates, and that distance is D. That we have, this distance is D. Okay, and A is obviously the area of the plate. So this is the area of the plate. So how much it can store, it will depend on the area. More the area, that means the capacitor is larger, it can store more charge, right? It can store more charge. But if the distance between them becomes large, it can store less charge, because it is inversely proportional. It will also depend on the permittivity of free space. Permittivity of free space. So permittivity of free space is 8.85 into 10 to the power minus 11. But what happens is that if I want to increase the capacitance, I can change the permittivity here. So if you remember, relative permittivity is equal to nothing but the permittivity in the material divided by permittivity in free space. So I can introduce a material in between the two plates. Maybe I can take air, or I can take paper. Mostly you'll see there are paper capacitors. So there is a paper. For paper, epsilon naught is not the value. Epsilon would be, or the permittivity would be nothing but epsilon naught into a value epsilon r. Epsilon r does not have any unit, because that is relative permittivity. Okay, so this is the permittivity of, let's say, paper. So if this epsilon is large, the capacitance will be large. So this is how human have developed, we have developed these electronic circuits, where even if we have a very small capacitor, not too large, it will still be able to store a large amount of charge. So it is said usually that if you're basically having a circuit, if you switch off the power, you should not touch the circuit, because what happens, the capacitor does not hold charge for a very long time. It discharges the charge, okay, through the pins. So it will discharge the charge, and if you're touching that capacitor at that point of time when it is discharging, definitely you are going to get that electric shock. Okay, the charge will flow through your body. So that is why, capacitors, in a way, bigger capacitor are more dangerous. More safety needs to be taken. Capacitor you might have also seen in tube lights. Okay, nowadays obviously we're using LED and LED lights and all. The technology is different, but if we look into a typical tube light, it will basically have something which we call as choke. Okay, and that choke is nothing but a capacitor. Okay, so if that capacitor is not working, you have to change it. For example, in a fan, many a times you will see there will be a ceiling fan which does not move very fast. Okay, it's slow. So if you make it at 4 speed or 3 speed, the speed does not increase, or the speed becomes very slow. Okay, and you call a mechanic, and that mechanic does nothing. He just changes the capacitor. It has got a capacitor. If you just change the capacitor, the fan will again start to speed up and work efficiently. Okay, so these kind of ideas are actually important, and you can also use them in your real life. Okay, so that's actually the story of capacitor, how they are used, and what are the important formulas. Q is equal to CV, and of course C is equal to epsilon naught A by D. So if you know the permittivity, if you increase the permittivity, you can obviously increase the capacitance of the capacitor. Okay, so just like resistor, capacitor can also be connected in series or parallel. Okay, so if you're talking about a resistor, and we can talk about, let's say, R1, R2, R3, and so on, and they are connected in series. Okay, we know that I can simply write it down as R is equal to R1 plus R2 plus R3 for a resistor. Okay, we can definitely prove it, but we are going to look into that later. But if we have three capacitors which are connected in series, this is not the formula. In fact, that's the parallel formula. The resultant capacitor would be 1 divided by C1 plus 1 divided by C2 plus 1 divided by C3. If the values of C1, C2 and C3 are given, you can do your calculations. Whatever value you get on this side, you take the reciprocal, that would be the resultant capacitance. This is C1, C2, C3. On the other hand, if we have capacitors which are connected in parallel, okay, they are connected in parallel, okay, maybe, okay, like this. And in this case, this C would be C1 plus C2 plus C3. So this is C1, C2 and C3. Okay, so always remember, in parallel connection, if you're basically, let's say, connecting it across a voltage source, let's say this is V, that means the voltage across C1, C2 and C3 are V, but the current will be different. It will be I1, I2, I3. The current is different, that means the charge will be different for the capacitor. If you look into the resistor, similarly, as I said, if I actually can draw a circuit here for a resistor, maybe, okay, I can take one resistor, two resistor, three resistor. I can take a power source, apply some voltage to it. Okay, this is my V. Now this is in series, that means whatever voltage we have will actually get divided. It will be V1 across this, V2 across this, V3 across this, in such a way that V is equal to V1 plus V2 plus V3. But what is the current? Current will be the same, because the current does not get divided. It has got one single part to follow, so the current will remain as I. Okay, so that means if I want to find out what is voltage V1, and let's say the resistance is R1, R2, R3, we know V is equal to IR. So I can, current remains the same. I can write it down as IR1. V2 is equal to IR2. V3 is equal to IR3. That means you can simply write it down as I R1 plus R2 plus R3. Okay, but what is V? V is equal to IR, right? So V is equal to IR. I can simply write it down as IR. This I and this I will get cancelled, and I will have R is equal to R1 plus R2 plus R3. This is how we can prove that if we have three resistors connected in series, the resultant resistance is R1 plus R2 plus R3. In a similar way, if you are talking about capacitor, these three capacitors are connected in parallel. Okay, so that means the voltage does not change, but the total charge will actually change. Okay, and using that result, we can show that capacitance would be 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 divided by C3. So, okay, in the last class I told you that dielectric, is a very important component in a capacitor. In fact, what happens is that I can actually use a dielectric to increase the capacity of a capacitor. So if you basically have a device, for example, it's a fan or a flash, camera flash, okay, it needs a lot of current to actually start at the beginning. So for that, a capacitor may be used, which will store that charge and let it go at a single time. Okay, so because of that, it will have that push or the current that is required to start the fan. Okay, so that's one of the main applications of dielectric, sorry, capacitor. But in order to improve the capacitance of a capacitor, there are a lot of options. Okay, so if you basically have a capacitor, let's say it's basically called as a parallel plate capacitor. Parallel plate capacitor concept we have already seen, but this is something which you should remember, because this will be even required later also when we are trying to prove Ampere's law and all. These things would be required for capacitors. So if you look into a parallel plate capacitor, what happens is there is a positive plate. Okay, what you can do is you can actually connect it with the positive terminal of a battery and the negative terminal or the cathode of a battery, and then these plates can be charged to positive and negative. These are conducting plates, obviously. Okay, and let's say these plates are separated by a distance t. Okay, so the formula for capacitance is, it's epsilon naught A divided by D, where D is the distance between the plate and A is the area. So a simple way to increase the capacity of a capacitor is either increase the area of these plates. That means more the area, more with the capacity. That means I have to make a very huge capacitor. Or we can also reduce the distance between the plates. But both of them has got some restriction. Okay, either I can increase the area to a very large space, but that will require large space. And if I'm using a smaller circuit, I cannot miniaturize the device. And on the other hand, if the distance is too small, there is a limit to that as well. So a third way to improve this capacity of the capacitor is to actually introduce a dielectric. Okay, so if you introduce a dielectric in between these two plates, you are basically going to get, if you're introducing a dielectric, you are going to get the increase in capacitance, and that increase would be epsilon naught A by D into K, where K is a dielectric constant. So in today's class, we are going to deal with this K and try to understand this. Okay, so if categorize material, you can have conductors, right, insulators, and semiconductors, right, semiconductors. But what happens in these three cases are that, if we look into the electric field that can pass through a conductor, insulator, or a semiconductor, you can actually categorize into four kinds of material. The fourth kind of material is dielectric. Many a times it's said that a dielectric and insulator is the same. The answer is not exactly true, because what happens is in a dielectric, it will allow the electric field to flow through it. So if you're basically having a dielectric material, the electric lines of force can pass through it. Okay, the electric lines of force can pass through it, and there are some very interesting examples of dielectric which are actually used in a capacitor. Okay, so this is a dielectric where we can actually have electric lines of force passing through it, as a result of which there will be polarization of charges inside. Okay, so if this is an electric lines of force passing through this dielectric, that means this side it's positive and this side it's negative. Now, a dielectric doesn't have too many charges which are free, because it behaves as an insulator if you are not passing any electric field. But if you are passing an electric field through it, and there are some free charges, okay, what will happen is towards the positive, the negative charge will go and towards the negative the positive charges will go. So what happens is you can see that there is certain thing which is called polarization of charges. So you can see positive and negative charges getting separated out. Okay. So what happens is in our dielectric we do have a polarization of charges where the charges are separated out. Polarization of charges. So when we talk about something like polarization of charges, it means that you can have the charges positive and negative separated out. Okay, it does not allow obviously any current. Okay, so one more important thing about this is maybe a question, does not allow current. It does not allow current. Okay, but it does allow an electric field to go through it. Okay, and that's the main idea behind dielectric, and that is what we can do and use it for. So next comes an example of dielectric. Okay, so if we are considering something like glass or mica. Mica is quite common, mica sheet. They're used as dielectric in capacitors. Okay, so if we use that, we can definitely have the increase of capacitance in this. Another idea of using the dielectric is, see, the capacitor, we do have a positive plate and a negative plate. Okay, and if we have a positive plate and a negative plate, that means the chances that the positive plate and the negative plate will get attracted towards each other, and the system might collapse. So this does not have a very good stability. Okay, that's important. So if you don't have a dielectric in between, it does not have a very good stability, because the force for this would be along this direction and this would be along this direction. As a result, unstable. Okay, so that means if we talk about the property of a dielectric, it offers stability to the system. That is also an application, because it will be a solid material. Okay, mostly it's solid. So if you basically have a solid material in between, these two won't get collapsed. And secondly, obviously, we can increase the capacitance. Increase capacitance. Okay, so that's the basic theoretical idea of a dielectric. Let's just go and check some numerical things here, or the mathematical idea of a dielectric. Okay, so what happens is that if you are basically having a dielectric, let me draw a straight field here. Maybe I will take this. Okay, this is the plate, and this is my dielectric in between, mica, glass, whatever. Okay, and the plates are you know positively and negatively charged. So let me say this is my positive and this is my negative. So in reality, it's not that you will basically have two plates and in between some mica would be inserted. That's not how it's constructed. An easier way of constructing is take a mica sheet, deposit a metal film on this side, deposit a metal film on this side, and then connect it with a battery. And that's how a real or practical capacitor is being made. This is for basically the understanding purpose. Okay. So if you look here, we know that the charges will be actually induced in this dielectric. Okay, so maybe we can talk about the charge density, the surface charge density. In this case, it's, let's say, plus sigma. On this side of the plate is minus sigma. These are the charge density. Now you have a dielectric in between. That means it does not have too many free charges. It's not that whatever positive and negative charges the dielectric has, all will be separated out. It's not that case. We can have an electric field, but that electric field will be less compared to the electric field outside. Okay, so let's say the electric field that is being outside, let's mark this as E naught because of this. Okay, but if you look into the dielectric now, the positive terminal, it will attract the negative charges. It might not attract all the charges obviously, and the negative charges will uh, attract the positive charges within the dielectric. So in this way, we're actually having a separation of charge. So what you see, that this is the external electric field, but there is also an internal electric field that is getting developed because of the dielectric. Okay, so this internal electric field that we have, is developing in this direction. In this direction, you can see. So this is my, let's say, EI. So this is the external field. This is the internal field. So what we see here is that this internal field will oppose the external field. But we also understand that this external field E naught is obviously greater than the internal field, because we have all the charges here on the surface, but in the dielectric the charges are less in number. Okay, so that's very important. So if you want to find out what is the net electric field between the plates, since EI is opposite to this, okay, we can write here between plates, this net electric field is equal to E naught minus EI. E naught minus EI. Okay, this is the net electric field that we have. Okay, and how different is E naught from EI? That change is actually given by something which we call as dielectric constant. So this is nothing but E naught divided by K. So this ratio is actually called the dielectric constant. Okay, so if I take an example, suppose this electric field that we have developed inside is equal to half of E naught. Okay, half of E naught. So if we take now E naught minus EI, I can simply write it down as E naught minus half of E naught. So this is E naught by 2, right? This 2 that we have written, this 2 is the dielectric constant, denoted by K. So that means E naught minus EI is equal to E naught by K. That means by how much the electric field is reduced is an idea which is actually given by the dielectric constant. So remember this. Okay, that's important, and you can see this is more or less a unitless quantity. Okay, so this is the actual idea behind dielectrics. Okay, so to remember this concept. So in a way we can say that this dielectric constant is actually nothing but the property of material. It depends on what material if you are considering. So if you're basically considering mica, the dielectric constant will be different. Okay, for paper it will be different, for glass it will be different, and so on. Okay, so that's important. Now we are just going to look into some variations, okay, some relation which is important, or property of material. Let me write it down first. Okay, so what happens is this. Okay, just a minute. So if you can see that this is actually a parallel plate capacitor, and we have already seen before that if you are considering a parallel plate capacitor and if you want to actually find out the electric field at a particular location, E is equal to sigma by 2 epsilon naught. Okay, and we have actually done a numerical where we have said that what is the field in between two parallel plate capacitors. Okay, let's see if we have it here in this particular slide, or I have run it somewhere else. Okay, okay, so we have done one problem for a parallel plate capacitor. Okay, if we have it here, yeah, this one I guess, not this one. Okay, let's quickly revise that because that is also important. Is it here? So what happens is, if you are having one parallel plate, the electric field is nothing but sigma divided by 2 epsilon naught. But if you are basically having two plates, this particular problem, if you are basically having two plates, and if you want to find out what is the electric field in between, we can say that because of this is sigma by 2 epsilon naught positive, so it's going in this direction. This is negative, so this is also going in this direction. So we can add them up, and the total field at the center would be sigma by epsilon naught. This formula or this relation that we actually have seen, we're going to take help from there. Okay, so if you're looking into the electric field because of a single plate, this is sigma by epsilon naught. But if we are considering the two plates, okay, if we are considering the two plates, so that means for the capacitor, that we are considering, it's nothing but sigma by 2 epsilon naught plus sigma by 2 epsilon naught. So E, let's write down naught without the dielectric, would be equal to sigma by epsilon naught. So don't get confused. This is very important. Okay. Also, we know that sigma is the charge density. Sigma is the charge density. So this is nothing but charge by area. Okay. That means we can write down this electric field within the plates without the dielectric as Q divided by epsilon naught A. Okay, these two are very important relation. We can use it later, but there might be some numericals to this as well. Okay, so these relations you have to more or less remember. This one we have already derived before. Okay, so that's one part. So if we use this relation, this is sigma. So what we can say is that sigma is, uh, or let me just write down what is my E naught, right? E naught is sigma naught by epsilon naught. Okay, or sigma is the charge density, so we can keep it as something there, as we can just keep it as sigma naught, or we can write it down as sigma only. Let's write down this as sigma. But when we are considering it inside the plate, the electric field Ei is nothing but sigma I by epsilon naught. Epsilon naught, epsilon, sorry, not epsilon naught, epsilon is actually nothing but the permittivity that we basically have, right? So let's write it down like this. So this sigma will be different because it's the charges inside the plate. This sigma would be different because this is the charges outside the plate. So charge density will definitely be different. Okay, so that means if we just find out what is E naught minus Ei, E naught minus Ei is nothing but E naught by K, we have just seen. So we can write it down as E naught divided by K is equal to, E naught is this. So I can write it down as sigma by epsilon naught minus sigma I by epsilon naught. Okay, so if you take that, we can in fact take the ratio here. Okay, you can take the ratio. So here, what was my E naught? E naught was sigma by epsilon naught. E naught was sigma by epsilon naught. So we can use this relation, sigma by epsilon naught K. Okay, epsilon naught K. So we can see that this epsilon naught, and this epsilon naught will more or less get cancelled out. Take the space. So that means that this sigma I that we have, that means the charge density of the dielectric is equal to, we can take sigma on the other side, so we can take 1 sigma here, this is within bracket, it would be 1 minus 1 divided by K. Okay, so this is the relation between the charge density inside the dielectric and the charge density outside. So charge density outside is sigma, and the charge density inside is nothing but sigma into I. Okay, so that's the very important logic that we have. Try to do this. So what happens is with the electric field with the introduction of dielectric. Okay, let's take these observations. Okay, the first observation is that the electric field decreases. Okay, we can see that. That means that electric field E naught, if it was original, after the introduction of the dielectric, it will become E naught divided by K. We have seen it in the last slide. Okay, now what we're going to do is we are going to look into the potential. So for understanding potential, I hope we remember that dV, okay, which was my potential dV, okay, potential was connected with the electric field using this relation E dot dx. Okay, we have already seen it in the electric field chapter. Okay, so in a general, if we want to know what is the potential at a particular point, we can see the direction between the electric field and this is a dot product. Okay, so that's the same direction, dx and E electric field is same direction, so that's cos 0 is 1. So I can just write it down as, in this particular case, let's say E naught is the electric field without the dielectric into the distance between the plate, which is nothing but d. So potential and electric field, this is the relation which we can use, but this is without k, or without the dielectric constant or dielectric, right? So it's in free space. But if we introduce the dielectric, let's say this is V, this E naught won't remain E naught, it will become E naught divided by K into D. Okay, this is with K, with K. Okay, so what is my E naught into D? E naught into D is V naught. So that means the potential will become V naught divided by K. V naught divided by. So what do we see? That even the potential decreases. Potential decreases. Just by knowing these relations, we can actually derive these points. Okay, so that's easy. So now what we're going to see is what happens to the capacitance. Okay, I said that the capacitance should increase. Let's see whether it really happens or not. So we can see that the potential will become, uh, okay, let me take this 0 out here. This potential will actually become V naught divided by K. Okay, let's see what happens with the capacitance now. Okay, let's see what happens with the capacitance. Okay, so if we look into the definition of capacitance, I told you, I think before, that capacitance is basically a constant for a system, and if you look into the typical capacitance, it would be nothing but charge by potential. Okay, let's say this is the potential or the change in potential or the small potential. So in general, if you're talking about a capacitor without the dielectric, it would be nothing but Q divided by the potential without the dielectric, so that is nothing but V naught. Now what we have done is we have introduced a dielectric, so I can write it down as Q naught divided by V naught divided by K. Okay, so if we write it down like this, I can simply write it down as Q by V naught into K. But what is Q by V naught? Q by V naught is nothing but C naught, right? So if we can write it down as C naught into K. Okay, so this capacitance that we have is without dielectric. Okay, and this capacitance that we have here is with dielectric. So we can see that this will actually become C naught into K. So what do I see? That C increases. Okay, C will increase with the capacitance. We are going to see what is the relation. We already know it. There are different ways of doing it actually. C increases. So C will become C naught into K. Okay, so that's the idea behind using a dielectric and how actually it increases the capacitance. Okay, we can also do it in an indirect way, in a longer mathematical form and try to derive it. Why I'm doing this? Because there might be numerical asked based on this particular topic. Okay, so just now we have seen that C is equal to Q by V naught into K. We are going to use all this relation. V naught is equal to E naught into D. So let's try to replace these results. V naught is equal to E naught into D into K. Okay, and what is my E naught? So if you remember, if it's a parallel plate capacitor, two plates, E naught is equal to sigma by epsilon naught. Sigma is charge density, so I can write it down as Q divided by A epsilon naught. That's my E naught. So let's replace it. So I can write it down as Q divided by Q divided by epsilon naught into A into D into K. So this Q and this Q will get cancelled, and I can take the epsilon naught on the top. This would be epsilon naught into A divided by D into K. A very important relation for capacitance. So let me mark this. This is how it is derived. If you know the logic behind this derivation, you can in fact solve a lot of numerical problems as well. Okay, this will come in handy. Now, if you look into this relation, what happens is if you're basically having air, okay, there is no change in the ratio. Okay, so let's say without dielectric, so we can, if we are talking about without K, okay, without K means we can talk about vacuum or even air. Okay, or air. So what happens is if you're basically having the plates here and you don't have in between anything, the electric field, okay, the electric field which is there is E naught, and there is nothing to oppose. So the electric field will remain as E naught. Before it was E naught, and after, because there is nothing, it will remain as E naught. So is there any change in ratio? The change in ratio is not there. That's why this is remaining as 1. So that means if you are considering the dielectric for air or vacuum, it is always going to be 1. Okay, and that's the idea that we have. So dielectric constant is basically giving me an idea on how much the electric field is more or less changing. So that's important. Okay. Now what we are going to do is we are going to introduce certain things within a dielectric system. Okay, maybe we can talk about introducing a metal in between. Okay, but before that, I think we have already discussed it, and there might be certain questions based on this as well. Advantages. Now this is a vast topic, so we have already seen this, right? Let me just write it down just once. Stability to plates, that's very important. Stability to plates. Okay, the prevents the plates from sticking, right? Prevents plates from sticking. One more advantage, writing it out in such a way so that you can prepare your notes from here itself, right? The most important advantage because of which we are using it is nothing but it increases capacitance. Okay, and number 4, it can actually prevent breakdown. What does it mean? If you're basically having not a dielectric in between, there can be too much charge that gets accumulated on both the plates. If you're introducing a dielectric in between, that will actually try to control the buildup of the electric field. It won't build the electric field to that much high value, as a result of which we can say that the electric field breakdown will more or less be prevented. Okay, so these are some very important advantages of dielectric. Now what happens if you're basically introducing, this might be a numerical question, what happens if you're basically introducing a metal, let's say. Okay, we are introducing a metal in between the plates. Okay, let me write down this question. Okay, the question is, what is K for metal? Okay, this has got a very interesting thing to do because we have already done so many topics and we know what happens in the electric field inside a metal. If you're basically having the dielectric plates and let's say we have got a metal in between. Okay, so in a metal, we know, we have already seen it for a solid sphere. Okay, conducting sphere, metal is basically more or less conducting, that the electric field that we have are never at the center, it is always at the edge. Okay, the electric field is always at the edge. Okay, so if you're basically having a positive and negative plates here. Okay, and this is my sigma plus, sorry, sigma plus, sigma minus, minus, or let me minus here, and this is my sigma I. The question is, what is the charge density for a metallic plate? Okay, so we know by the formula that sigma I is equal to sigma into 1 minus 1 divided by K. Okay, now if you want to find out K, we have already seen what was our result for E net. The net electric field is always equal to E naught divided by K. But if you look inside the metal, okay, it's not that it's a dielectric. What happens is the amount of charge that gets developed on the surface of the metal, it will also have no charges. It will become separation of charge. It will become positive here. In between there are no charges, only at the edges, and it will be negative. But metal, it's a conductor, it has got free electrons, so the number of charge on the plate will be equal to the number of charge on the metal. And what was our E naught? E naught was nothing but E naught minus EI, but this will be equal to 0 because EI will be equal to E naught. Whatever is the field on this side, whatever is the field on this side, the same field will be developed in the opposite side as well, because the number of charges in metal equal to the number of charges on the plates. So that means this is 0. So that means the E net is 0, which is E naught divided by K. Now this part can only become 0, is 0. Okay, this is the logic, only if K is equal to infinity. If K is equal to infinity, that means if the dielectric constant is infinity, then only we can have this part as 0 mathematically. Okay, so what does it mean? Therefore, we can also find out what is the charge density. Charge density sigma I is equal to sigma into 1 minus 1 by infinity. 1 by infinity is 0. So that means the charge density in a metal inside these two plates is equal to the charge density that is developed on the surface. So that's a very important thing. Okay, so what do I say here is that conclusion for a metal. Okay, this K is infinity and the charge density is equal to sigma. Okay, so we have to remember this. Why? Because there might be numerical problems on this, based on which we can actually use this formula, and based on which we can actually solve some problems as well. Okay, so before we end, let's try to take at least one or two problems. Okay, and there are different ways of solving problems in this. Okay, you can actually have different plates. Okay, let me just do one sum. I hope we can have that much time to actually finish this up. Okay, uh, the topic might be, let me just see. There are different ways of giving this. There can be different kinds of numerical problem. I'm sure if this is in the syllabus, you're going to get something some questions based on this. Capacitor with partially filled dielectric. Partially filled dielectric. So that means the entire space is not filled. If the entire space is filled, we know if the entire space is filled, we know with a dielectric, the capacitance would be epsilon naught A divided by D into K. That's very simple. But what happens if it is partially filled? Partially filled means you are going to have some part empty, some part a dielectric, or maybe some part empty and some part you might have metal and some part a dielectric. So anything might happen. Okay, so we do have a dielectric plate like this. Let's say, let me just draw one dielectric in between. Okay, we have one dielectric in between. Okay, and let's say that the thickness of this particular plate is T. The thickness of this particular plate is T. Okay, and the width of the plate, or the distance between the plates rather, is D. So that means the distance of the empty space is D minus D, right? So this is my positive plate and this is my negative plate. Okay, so this is my dielectric, and this will be the electric field that will actually get developed here. Okay, so we have the electric field here as E naught, and because of the dielectric, the electric field would be E naught by K. This will also be in the same direction because we have already considered the two directions, and after that we are getting it to be E naught by K. So for because of the dielectric, the electric field is E naught divided by K. Okay. Now I want to find out what is the value of C. It's obviously not going to be K because there is some empty space and some space which is actually having a dielectric. For doing that, we can actually do a very simple idea here. We can talk about potential first. We know that potential is equal to nothing but E into D. So there are two parts to the potential. First is here and second is here. Okay, so let's divide this potential into two parts. Because of the first electric field where there is no dielectric, the distance is d1, plus the electric field where there is a dielectric and the distance is d2. So we can simply write down, in the first space where there is no dielectric, the electric field is E naught, and distance d is d minus t. The distance d1 is d minus t. So we can simply write it down as d minus t. That's how you solve these problems. Okay, plus E2. This is the electric field here. Electric field in the dielectric is E naught by k. So it would be nothing but E naught divided by k into d2, which is the thickness of the plate, which is nothing but t. So what we can do is we can take E naught common, and I can write it down as d minus t minus t by k. Okay, plus t by k. So I've taken E naught as common, right? But what is my E naught? E naught, we have already seen, it is nothing but sigma by epsilon naught, sigma by epsilon naught, right? This one you always have to remember. E naught for a parallel plate is sigma by epsilon naught. Sigma is q by a, so it is q by epsilon naught. Okay, so we can do that, and if I write that down here, okay, I can simply write it down as q divided by epsilon naught a into t minus t plus t divided by k. Okay, so we can actually find out q by delta v here. So if we do that, we have got delta v on this side, delta v on this side. So I can write down this as q by delta v. So q by delta v will come here, so I'll cross multiply, epsilon naught a will go that side. So I can simply write it down as epsilon naught a divided by this term. So this is d minus t plus t divided by k. Okay, so which is nothing but my capacitance. So this is my result for capacitance when basically I'm using a dielectric. So it's partially filled with dielectric, and partially it's empty. So I'll take D, which is the thickness of the plate, minus T, thickness of the plate, dielectric plate, plus T by K. Okay, T is the thickness of the dielectric plate again, and K is the dielectric constant. So this formula we can actually use to solve it. There is another way to solve this problem. Uh, I think we should discuss that also, because if we are able to solve it in different ways, we'll see that during exam you have got other options of solving this as well. Now you see these two plates which are there, we are actually considering that there are maybe two plates here. Okay, this is one capacitance, this is one more capacitance, both of them are connected in series. So let's say uh, okay, let's do it in this way. Okay, it's not complicated. I hope you understand this. We have got two capacitors here. It's equivalent to C1 and C2 in parallel. Okay, so if you recall, if we have C1 and C2 in parallel, just opposite to resistor, the equivalent capacitor is 1 by C1 plus 1 by C2. Okay, so here also we can do the same thing. So we can write down 1 divided by C, which is the resultant capacitance, because I want to find out what is the capacitance here. 1 by C1 plus 1 by C2. Okay, and what is my C again? C is equal to epsilon naught A divided by D, the distance between the plates. Okay, and if there is a dielectric, I'll put a K there. For the first part there is no dielectric, so I can write it down as 1 divided by epsilon naught A. The area of the plate will more or less remain the same. Okay, divided by D. D is the distance, so the distance of the length is D by D minus T, so I can write it down as D minus T for the first part, plus 1 divided by C2. For C2 the distance bit is T, T is the thickness, so I can again write it down as epsilon naught A, area, cross sectional area is this, it will remain as A, divided by, in place of D I have to write down T, because that's the thickness of plate, into K, because that's the dielectric constant of the material. Okay, so if we just simplify this, I can write it down as D minus T divided by epsilon naught A, plus this would be T divided by epsilon naught A into K. Okay, so what I can do is I can write it down as T divided by K. Let me write it down as T divided by K. It will make things simpler. So that means I can write here this as T divided by K. So what we have here is 1 divided by epsilon naught A as the LCM. It will be D minus T plus T divided by K. This is 1 by C. This is 1 by C. Okay, so this implies my C is equal to just the reciprocal of that. This would be epsilon naught A divided by D minus T plus T divided by K. So you can use either of these methods to actually find out the total capacitance if you are introducing a dielectric in between. There can be so many questions on this. You can have this is introducing a dielectric. You can have a dielectric and a metal filling up the entire space. You can have a dielectric, a metal, and then you can have empty space. That is also possible. You can have empty space, one dielectric with dielectric constant K1, another dielectric with dielectric constant K2, and so on. For all of them the approach more or less remains the same. You can consider this, it will be more easy, it will be a faster calculation, or you can use this technique as well. Okay, so both these techniques should work and you should be able to get the answer. Imagine you've got a dielectric, uh, another dielectric whose constant is K1, so this would be D minus T plus T by K1 plus T by K2, and so on. Okay, thickness are different than T1, T2, these things will also come up, so you will be getting the formulas modified accordingly. So in this, capacitor filled with dielectric, if we are having a partially filled dielectric system. Okay, it's not that the entire space within the two plate is filled with dielectric, might be it's partially filled. Okay, we did also observe that if we're considering a metal, the dielectric constant K is equal to infinity. Okay, so that's there. So based on this, we can actually take up one more problem. Let's see. Just try to do this particular problem. Here, what I'm saying is that I'm basically having, okay, uh, a space, obviously, okay, and then here I have got two things. One, I have, let's say I've got some dielectric of thickness T, and another is a metal, let's say. You can have different kinds of problems in this particular topic, but it all depends on what problem they want to give you. But mostly it's like this. Okay, so this is also T, this is also T, and let's say the space between the two plate is D. Okay, so now we can see that there are two plates inside, and also there are some empty spaces. Okay, so let's say this is my dielectric. So if this is my dielectric, let's say the we know that electric field would be E naught by K if it is a dielectric, and let's say this is my metal. That means the dielectric constant is infinity. Okay, so let's say this is my metal. Okay, this is my metal, and the rest of the space is empty. So in the rest of the space, the electric field is E naught. Okay, so as I said, there are two techniques to do it. First, what you can do is you can take the potential, you can add them up, do your calculation, then you should be able to get your answer. But in order to do it faster, you can also use this technique where you can say that these capacitors are in series. Okay, and if you actually want to draw a circuit, we can do it. First one would be this of thickness T, the second one may be of the metal, and the third one is the empty space. Okay, so that means if you are considering this, first one might be of E naught by K. So let's say it is E naught by K, that dielectric. Second one is K is infinity, and the third one is the empty space that the electric field is E naught. Okay, so these are the three dielectrics we have. Let's say they are connected in series, so that means we can take 1 by C is 1 by C1 plus 1 by C2 plus 1 by C3. So if you do that, I can obviously take a reciprocal of this. Okay, but before doing that, we can put up the values. As I said, this C, the technique will remain the same, epsilon naught A divided by whatever is the thickness. So let's say C1 is for this, so it is 1 divided by epsilon naught A divided by the thickness is T. Okay, and if it's a dielectric, it is C naught in empty space, and if it's a dielectric CK, it is epsilon naught A by D into K. So I'll write it down into K. So that's the first one. Second one, let's say this is the metal, 1 divided by epsilon naught A divided by, here also the metal thickness is T, into, now K in this case is infinity, very high, plus 1 divided by, here for this third one I can write it down as epsilon naught A divided by, now whatever is remaining is the empty space. Okay, so that means for C3, the third capacitance, it is nothing but D is the total length minus, this is T, this is T, so 2T. So that would be the space. So I can simply write it down as D minus 2T. Okay, so you see this is 1 divided by infinity, so this part is 0. Okay, so I can simply write it down as this is, it can be written as T by K, so I can take T by K on top divided by epsilon naught A, and then plus I can write it down again D minus 2T divided by epsilon naught A, right? So we can take 1 divided by epsilon naught A, and this would be T minus K minus or plus D minus 2T, right? So we can also write it like this. Therefore, what we can have here is C is the reciprocal, so that's epsilon naught A divided by T by K plus d minus 2t. Okay, so that's my relation for capacitance in this particular case. How it is different from the previous case, because the metal is not contributing to the capacitor, but it is eating up the capacitance of the system. See, if we look into the previous result, okay, we said that it was d minus t plus 2k. So this is d minus t. The capacitance is reducing because of this. This is d minus t. But in this particular case, it is d minus 2t. Okay, so that's the difference that we have. So that way we can actually solve. So you can have anything inside in between. You should just know what is it for metal, what is it for capacitor, and then so on. One more problem might be we're not doing it. Maybe we have got two plates, two dielectrics inside. One will have a dielectric constant K1, the other one might have K2, okay? And then you have to find out what is the resultant. You can use this technique and you can find out the equivalent capacitance for any kind of system, okay?